Dear Professor, I'm Gao Shenghan. I would like to submit my homework for midlearning and MATLAB simulation of spring temperature system. Next, we have six part about part one. Part one is the main content. Part two is the schematic diagram of the system structure. And the T part is the derivation of the time domain model and the transfer function in the Laplace domain. And the part four is MATLAB modeling. The five is analysis of simulation results. And the sixth part is summary and demonstration. And next, the part one is the main content. We get a picture. Spring demo is a simplification of what happens in many real mechanical systems and is a common part for suppression units. So we have two questions about one, create the time domain model, then Laplace model to create the transfer function. And the question two is create the MATLAB model, then show the plot for sitting time and system response. And next is the part two, systematical diagram of the system circuit. So we can first we can look at the systematical diagram of system secure circuit. As we can see from the figure on the left side is a damper, labeled as damper B, which is connected to the wall. On the right side is a load, and the electric force Ft acts on this node. At the same time, the node is also connected to the mass M. And after understanding the system structure and mechanical relationship, we can drive the time domain model based on Newton's signal law. Newton's signal law tells us that the acceleration, acceleration of an object is theoretical, proportional to the net force acting on it and inversely proportional to the mass of the object. And coupling with the mechanical relationship is Ft equals F1 plus F2. And from the previous page, substitution the damping force F1 equals Bxt and F2 equals mxt. And the part T is having obtained the time domain model. The next step is to transform it into the Laplace domain to get the transfer function. Under their integral conditions, take the Laplace transform of both sides of the time domain model. According to the properties of the Laplace transform. The Laplace transform or gives and after transformation it gives us this, and origin can get this, and so GS equals this, and the substitute equal 1000 and B equal 50, so we can get this. And the next, the code is next part is this code fully realizes the modeling and analysis of the spring damper system from parameter definition, model construction to response calculation, calculating, and performance analysis. It clearly demonstrates the dynamical charge of the system under the step force, providing intuitive result for understanding the system behavior. Next, I will analyze it paragraph by paragraph. And the first, this section of code defines the core physical parameters of the spring damper system. The M and the M and the BF equals for 3 number, and the two step is based on the parameters. The transfer function of the system is constructed. The long after long and the dn correspond to the formulas the word, and the as well as is system model that can be recognized by MATLAB, which is the key to connecting system and simulation. And the steps T is set the simulation time longer and calculate the response T. Defines the time access from 200 seconds. The step function calculate the displacement response under 500 new step force, and the Y and the corresponding time T out. Next is the fourth step, initialize the response data. The plot function is used to draw a curve of displacement changing with time. Knives and grid make the curve move readable. Actually, presenting the dynamic change of the system. And the fifth step is calculate and output the system performance First, determine the theoretical state value and against its demonstration. The step in for function is the response to obtain the setting time. Use FPRNTF to print the results, and the quantification of performance. And next, we can look at the simulation result in MATLAB. First, consider the relative response curve. From the curve, we can see that the relative shows a moderately increasing trend as time goes by. It finally stabilizes at 10 me 1 second and 10 meters 1 second, which is constant with this steady state velocity. And from our actual solution, we're applying the correctness of the simulation result. Next, look at the displacement response curve. The displacement shows an approximately linearly increasing terms as time increases. That is to say, the displacement will continue to increase with time, and there is no stable limit value. That's all my homework for. Thanks for watching.